Welcome to this week's Learning Machines seminars at RISE. Today's speaker is Megan Stanley. She is a researcher at Microsoft Research Cambridge. She had her PhD in physics from the University of Cambridge in 2017 and works on machine learning in the sciences, especially with regards to few-shot learning and generalization. The topic today is molecular property prediction using few-shot learning techniques. The seminar will be recorded, and if nobody objects, for example, by sending me an email, it will be published on YouTube afterwards. With that said, I will hand over to Megan. The floor is yours.
Thank you very much for the nice introduction. And I also wanted to say, if you have any sort of quick clarification questions during the presentation, please just yell out and ask. I'm very happy to take questions then, and if you have anything longer you want to discuss, then we can also have a longer discussion at the end. Cool. Okay, so as we said, I'm going to be talking about work that we did that is at the intersection of drug discovery and few-shot learning techniques, and also some other bits and pieces of machine learning in there. And just to give a quick outline of the talk, I'll start by motivating the relationship between machine learning and drug discovery, which in some ways is a topic that has been, let's say, explored for quite some time, but it's recently the way that is being approached is perhaps becoming a little bit different. I'm going to talk about, what are some of the very specific challenges and how it's possible that few-shot learning can be very useful there. And one of the things that came out of this work was the need for, as always in many of these machine learning settings, the need for good data sets and clear benchmarks. So to motivate the discussion a little bit, for anyone who doesn't have any kind of like biology or chemistry in the background, let's look at a very simple idea in drug discovery. So we can think of a protein which is this green blob here, as a machine for affecting some kind of change in the cell by acting on other proteins or acting on the small molecules that I've drawn here as little red blobs. So you can imagine that, for instance, you would start out with a protein in an inactive state and it's unable to do anything. But it can be switched into an active state by the binding of a small molecule, which is this turquoise green thing here, into its active site. And that will effectively alter the conformation of the protein and trigger transformation processes downstream. So there's a cascade of effects. So this can be not just restricted to having some effect, changing some small molecule, but it can do all sorts of other things in the cell. And this small molecule I will be also potentially referring to as the protein's ligand. So when we're designing a drug, when one is designing a drug, not me specifically, what you're looking to do is find small molecules that bind very specifically into that active site and alter the conformation of the protein and affect the change that you want. So you're coming up with this very specific tool to adjust cellular machinery. And although this is a cartoon, it captures something really important, which is just the degree of this specificity. It needs to be quite a precise fit. However, the targets, these proteins, are incredibly diverse. So there are estimated to be between 80 and 400,000 different targets, different proteins in the human body, potentially that you would want to act on, without counting, pathogens as on top of that. And the space of possible drug-like molecules that you're searching in is estimated to be of order 10 to the 60. So it's a huge search space. So how does the drug discovery process work? Well, one way you can look at the very, very early stages. You'll have some knowledge of the target protein, and chemists will design a whole bunch of possible molecules that could be a hit and synthesize them, test them to see if they have any effect, and throw away the many, many failures. So this kind of funnel that I've illustrated here is meant to illustrate the high throughput screen. So this is when you have absolutely no idea what you need to start with. So you're querying quite a large section of chemical space effectively in the lab, and you'll expect to find very few molecules that will seem to interact at all. But once a hit is found, the basic backbone of that molecule is something around which you can optimize. So the whole process, the initial hit candidates are optimized in these iterative rounds of synthesis and testing in the lab long before actual in vivo testing can take place. So it's got a laser pointer here. So this is sort of an iterative process where you synthesize something, you actually have to go and test it in the lab and so on. And as you can imagine, this is taking this process around the loop many times is extremely time consuming, very slow, takes billions of dollars, hundreds of people over 10 years. And this is one of the reasons that lots of drugs can end up being quite expensive. Now, of course, in the value of this, in all of this, the value of computational approaches hasn't been completely ignored. There's a complex interplay at all stages, and many of the steps that happen in the wet lab are mirrored and complemented by things that people do computationally because it's faster and less expensive. So for instance, in our wider project, we've been looking at generative modeling of drug-like compounds to make good suggestions for possible molecules. For example, you could use a VAE with a decoder constrained to generate new graph components that's conditioned on some partial graph you've already suggested. But in general, you have to then automatically score the generated molecules that you've created against the desired properties in silico rather than testing them in the lab. And for that, you would want to be able to do this in a very rapid way so that you can then go and just only test the most promising candidates in the lab. So in other words, the generative models are in very tight feedback with the scoring models, but it requires that the scoring models are extremely accurate, because it's been shown that if your scoring model is interrupted or damaged in some way, or it's quite poor, you will end up with incorrectly assigned scores, incorrectly generated molecules. The models will generate molecules based on spurious correlations. So that's very unhelpful. Basically, we want very accurate property models. So disruption to this kind of feedback loop is a key problem in generating molecular suggestions, and it prevents this process being fully automated. So what you would actually want is you would want the small amount of in vitro data, the actually real world measured data, being fed back to improve modeling and optimization being automated towards an ideal molecule. But if your scoring model is wrong, that's not going to happen. And at the same time, one big problem with this that's often kind of slightly ignored is that if your property scoring models are quite poor and you're generating really bad suggestions, medicinal chemists stop trusting you. And they say, well, this computational modeling is nonsense, so we're not going to bother using it as much. So this is generally quite bad from a use case perspective as well. So okay, at the same time, we have to remember that this is a multi-objective optimization problem. So it's necessary to produce a drug that is affecting its specific target. It's also necessary to ensure that it's not acting on some other targets in the body. So there could be other protein receptors where if your drug interacts with them, you're going to produce toxic effects, and this is generally quite bad. You also want it to be synthesizable, so it needs to be something that can actually be made in the real world. And then it might have these other physiological properties. So here I put a little bit of a cell membrane to indicate this is something that you would want to be able to diffuse through a cell membrane and actually interact appropriately with physiology. So during this talk, I'm really focusing on this very specific problem of predicting drug-target interactions. So in other words, what is the activity of a potential drug? How is it interacting very specifically with a target? Okay, so how do we treat molecules in machine learning? What do we do with them? How do we input them to models? And we're all used to seeing these kind of graphical diagrams of molecules. So the question is, what do we do then? And there are a number of different ways of doing this. because applying machine learning in molecular property prediction is not a new idea. Quantitative structure activity relationships, or QSAR as it's known, have been predicted using a variety of techniques such as random forests and KNNs and MLPs for some time. And more recently, people have been describing them directly as graphs because seems a very natural way of looking at them. So one way of describing molecules precisely is the so-called SMILE string. So this is generated by first breaking all the cycle, taking your graph, breaking all the cycles in it. You identify the longest backbone chain and walk along it, recording the atoms until you reach a branching point. You then follow the branching point to the end and then repeat. And so you end up with this sort of trying to traverse the longest backbone, but chasing each branch to the end. And so this is sort of a consistent way of recording a molecule as a string. And this, as I say, renders it as a unique string. And then there's a whole body of work around using natural language models to operate on these strings. Again, for a range of tasks from property prediction all the way through to generation of new molecules. And surprisingly, this works quite well. And this is work from one of my colleagues demonstrating exactly that. So a string representation, particularly one that involves breaking cycles, isn't terribly natural. So perhaps a more traditional method is fingerprinting. And there are lots of algorithms for actually doing this, for encoding a molecule into a vector. But the basic idea is always the same. You choose a chosen vector size, you assign a descriptor to each, or effectively a number to each node in the graph. And for a radius of interest, you aggregate the local neighborhood onto each atom. And then you iterate that up to a maximum radius, and you use the resulting value to set a specific bit in the bit vector that you want. And there are many different ways of doing this. The one I will be using most commonly is called ECFP4, but generally these are known as fingerprints. And then, of course, more recently, with the advent of graph neural networks and the fact that molecules are so obviously and naturally, in some ways, graphs, graph neural networks have become more popular. So here we assign atoms as the nodes of graphs and bonds as the edges. And in the models that I've been using, we've actually had 3 different edge types representing, so this is L here, representing the different types of bonds, single, double, or triple. And we also choose an initial set of features using the atom types, their degree of bonding, their charge, and so on. And so just as a quick rundown of how a graph neural network roughly works, the typical scheme proceeds by running through a number of layers, each updating the node representations to new hidden states. So at each step seen at a single node takes the neighborhood node features and the edges and computes a message from all of the neighbors. And then at each node, the messages are combined with the current node by some update function. And finally, in order to obtain an entire graph representation, you actually also need an aggregation, a readout step here. And what we're actually tending to do is just take the mean over all of the nodes. This is a permutation invariant operation. Well, it doesn't matter anything about the ordering of the nodes or how they're arranged in space. The mean is taken, and this represents our entire graph. So there's a very rich zoo of approaches as to how to actually implement these updates and update and message passing steps. And it's one of those things where you can choose whatever seems most appropriate to the specific task at hand. And the variation that I focused on most involves concatenating the node and hidden neighborhood states, passing through an MLP, applying a simple nonlinearity, and making sure that we normalize to reflect the differing degrees of the nodes. So I've given a few references for some example cases, including those applied to molecules in particular, because that is not a new idea. These have been used to predict the properties of molecules, But what I really want to stress for the rest of this talk is that predicting calculated properties, as seen in much of the current literature, is not equivalent to predicting protein binding. So that there are data sets where the properties that are predicted are things such as the gap between energy levels and other things which can be calculated in principle with quite high accuracy from the molecular structure itself in the absence of further information. And this is still a very challenging problem, but it's one nice thing about it is that it's very possible to generate accurate training data in quite large quantities. So predicting how well a protein and ligand bind is a much harder problem computationally, to the point that doing it with high accuracy fast enough is actually currently prohibitive. So when I say fast enough, I mean fast enough that it can be included in the loop in an optimization problem. Sorry, is there a question?
Yes, there is a question. So I'm wondering, you went through all these kinds of input representations from smiles and all the way to using the whole graph for the graph neural networks. Are all these still relevant, or are some of them being sort of replaced by others?
So this is a really good question, because you would kind of think, well, some of these seem very, very simple, but actually the fact is at the moment, even now, all of them are being used by different groups in different ways. Somewhat surprisingly, I would say, but yeah, they're all still very much relevant. And I also didn't include, but I could have included an additional kind of class of descriptors, the most famous of which is CDDD. So this is continuous data-driven descriptors, where effectively what someone has done, someone called Robin Winter actually has done, is take something, it looks a little bit like a VAE, it's not really a VAE, it's an encoder-decoder model, and had it translate from a string to an output, a smile string to an output structure. I think that was the right way around. But the fact is that there's a latent space, and they use the latent space of their model that's been trained on a large number of molecules as a descriptor itself. And that's been shown to be a really good input featurization for quite simple random forest models. Yeah, so there's a wide range, and they're all still in use.
The jury's still out.
Yeah.
It will be the best way.
Very much so.
May I interrupt?
Yeah.
Are we talking about the one-dimensional, two-dimensional structure, or did you take into the consideration 3D information of a drug?
Right. So all of this at the moment is done without respect to the 3D information. There are approaches that sort of do try to include that as well. But yeah, that's not, I mean, that, yeah, it's just an extra choice. It's not immediately clear it does help in this specific problem. But yes, that is also something that has been done more recently.
Thank you.
Yeah. Yes. So where was I? The predicting, as I say, predicting how well a protein and a ligand bind is a much harder problem computationally. And of course, there are approaches that sort of use things, basically docking and free energy perturbation methods that try to do this. But they are very slow, and they are in some, I say very slow, they're relatively slow, and they are in many cases of limited accuracy or limited generalization, depending on which method you're talking about. And one of the challenges is that you have to have quite a lot of information in advance about the target protein. You need to really know which location on the protein that you actually think is the active site. You need to set everything up before you try to run one of these docking or free energy perturbation calculations. That's not always something that you have access to as well in this sort of early stage drug discovery setting. So really, the very specific setting that we're seeking to fix here is The data that we have to learn from are real laboratory measurements. They've got many sources of noise, whether that's measurement apparatus, odd distributions in chemical space, because they've been generated by a chemist sort of following their nose and doing their own optimization that they think is appropriate of that backbone. There's variation from lab to lab and test to test, and there tends to be, very importantly, an extremely limited number of data points, because at the end of the day, these things have to be synthesized by hand and tested. So let's see what happens when we take some real data regarding a particular protein target. So it looks like this. And apply a collection of approaches and really try to do our best to predict whether or not a proposed test molecule will work. So just an idea of what the data looks like. It literally is just a set of molecules and some labels here. I've turned it into a binary classification problem. Does this ligand actually have activity against this target molecule? And so in this plot, what I'm showing is a single protein binding task. So a random forest model is supplied with fingerprint features, and this is a very typical setup that's used by chemists in a pharmaceutical company. And I'm allowing the model to actually access differently sized training sets. So sometimes they will only have access to 16 data points, and then I'm sort of giving them training data sets that increase in size so that I can look at how this changes with the amount of data available. And rather than the area under the precision recall curve, I'm plotting the difference between that and the proportion of active molecules in the data set, so that a model achieving 0 on this graph, a flat line here, would be no better than a random classifier. And clearly this modeling hasn't been terribly successful. Not only is the model unable to learn enough without more data points to make useful predictions, even with very few data points, it performs even worse. So what happens if I, try a different protein? Maybe that was just a particularly bad example where, for whatever reason, the data was really bad and it was just very difficult. So if we try another task, we might actually see that we're doing quite a lot better. So if I supply more data to the model, I'm getting an improvement in my performance. But we can still see that in this sort of lower data regime, things are still quite bad. In fact, I would argue even in the high data regime, we're not doing fantastically, but it's really bad down here when we're only having a few tens of molecules. And this is very much the realistic amount of data that you have in one of these early stage drug discovery projects. So I've mentioned that there are a number of other possible methods for modeling this scenario, for example, k-nearest neighbors on top of the fingerprints, or perhaps training graph neural networks. So if we take this previous good example that I showed before and apply both of those methods, well, actually, as it turns out, random forests operating on top of these ECFP4 fingerprints are doing actually quite well, and the other methods are not, even if we try quite hard, are not performing terribly well at all. So this is a little bit disappointing and quite worrying as well, because we know that we're always going to be stuck trying to use models in this data regime to have in the loop in our generation process. So what can we do about this? So in general, it's obviously a really challenging problem. The data is noisy and the data is very small. But pharmaceutical databases contain many project data sets. And some of them will be containing data from actually very similar targets. So they might have proteins where they are not precisely the same, but they have very similar structures at the end of the day. There might be binding mechanisms that are conserved. So we might hope that what we can do is learn more general information from ligand binding behavior from this kind of data. So in other words, can we leverage the fact that we've got many tasks? So this suggests that we might be able to treat this as a few-shot learning problem. So we want to be able to learn to predict from very few data points. So to do this, we actually have to pre-train on the data that we have available for many tasks. And then when we have a new drug discovery project, we take our pre-trained model, our few-shot model, in whatever form it is, we take the small amount of data from our testing task and we use that to adapt the model so that we can now use it in the task of interest. So that's the kind of setup. We have the pre-training stage with many tasks, all for different targets. We have a fine-tuning or adaptation stage, and then we can test out how well that's worked. And we want to evaluate how effective this procedure is for tackling the problem specifically of protein ligand binding prediction. But of course, we're not restricted to only using it in that setting. It's just, in this particular case, that's actually quite helpful because of the similarities between the different tasks. So for this to be set up as a few-shot learning problem, we need to sort of set it out correctly. So what we need is a trained set of tasks. We need a test set of tasks, which here is dtest, so detrain, detest. We're also including a validation set of tasks, which we're going to use to ensure that we've chosen the correct hyperparameters for our meta learner or our few-shot learning model. I'll come round to why I'm using those two different words in a minute. And each individual task is then itself composed of actually a number of data points. So there'll be the support set or the training data for the task and the query set or the test data of the task. So this is a very sort of standard meta-learning setup if you have read meta-learning literature. So with this framework in mind, how might we go about modeling? What are the types of models that we can use? So there are 4 categories. There are the baseline methods. So these are single task methods, which actually have none of this few-shot learning involved. You are just taking the support set data for a task, using it to train your model, and then testing on the query set or the test data of the task. So those are my baselines. There are self-supervised pre-training models, gradient-based meta-learning and multitask learning models that I'll discuss. And then finally, metric-based models. In this, I include prototypical networks. I also have put neural processes in this box, although that's not quite, but they're very much related. So that they sort of, I think, go together. So broadly speaking, gradient-based and metric-based few-shot learning fit into the previously described framework and can be thought of as episodic. So in each training step, you're addressing a batch of tasks from the entire set of training tasks before fine-tuning on a new task at test time. The other methods proceed either without pre-training or by pre-training on a large unlabeled set of molecules. So let's focus on these proper few-shot learners. So in multitask learning, a shared model component along with several task heads are trained together in an episodic fashion. So each batch of data draws example molecules from several tasks drawn from the training set. And this aims, in our case, to train a shared GNN to extract good general representations for use in protein ligand binding prediction. So here I have a GNN model and I've got a bunch of task heads. Each of these represents a binary classification problem for the different training tasks. And then at fine-tuning time, the shared GNN is kept fixed and a new task head is adapted using the support set of the testing task before evaluating with the query molecules. In fact, you can also fine-tune the shared GNN as well, but that's a choice, effectively a hyperparameter choice as to what the relative learning rates across those two models should be.
Could I ask a question?
Yeah.
So are all the training tasks protein binding tasks?
Yes.
What is it? Is it binding affinity, which have been discretized?
Yes. Yeah, so I haven't gone into the details yet of the data set, but this is a binding activity prediction, so based on IC50, and then it's being converted into a binary classification problem for now. So
Thank you.
An adaptive threshold, yeah. So in model agnostic meta-learning, this similarly proceeds by using batches of training tasks in this episodic fashion. However, each task is used to adapt a copy of the model. after which the query set is used to probe the gradient at the model's new location in parameter space. And then the resulting gradients are gathered and applied to the original model. So it's this kind of two-gradient, two-step component in model agnostic meta-learning and the associated methods. The aim overall is that eventually the model will occupy a position that adapts most quickly. So that is with a small amount of data and very few steps, most quickly to a new task. So this is an idea originally proposed by Chelsea Finn at Stanford, and then there have been a number of adaptations, different versions of this paradigm suggested since. And at adaptation time, again, the support set of the task, or as we call it, the training set, is used to fine-tune the model prior to its evaluation. So at the bottom here, I place the overall objective of the training procedure, minimizing the loss over a batch of tasks following some initial adaptation. And again, this represents the hoped for result at fine-tuning time, and using many batches of tasks represents maintaining diversity in the tasks over which you want to specialize. So prototypical networks, on the other hand, are rather different. The overall objective is to make predictions of the query set or the target set labels in the context of the support set data. So query and support set data is passed to the model at the same time. Prototypes for the classes are obtained. So prototypes are the encoded representations of the molecules for the positive and negative classes. They're obtained from the support set or the training set molecules. And the query set, or in other words, test set molecules, are assigned labels based on their similarity to the prototype. So in reality here, we actually use the Mahalanobis distance, and you can use the Euclidean distance or something similar. But we wanted to, I thought the Mahalanobis distance is useful to maintain enough information in the distribution over the support set molecule representations. So that was just the reason for that particular choice. It's been shown to work quite well. And neural processes are very similar, but rather than using a metric to measure similarity directly, the query and aggregate support set representations are all concatenated before being passed to a final decoder model to make a prediction of a single test set molecules class. And finally, the self-supervised pre-training takes inspiration from some similar tasks in NLP. So we use both prediction of randomly masked node features and as well as this context prediction, which we can go into more detail at the end if people want to, but in the interest of time, I'm going to sort of move over that for now. So basically, a surrogate GNN is used to find a representation of a disconnected context for a node. And then the prediction aims to get the context of that node correct. Sorry, skipping over that. When we looked around, sorry, I'm slightly confused. The colors have gone all strange in my next slide and it's worrying me, but hopefully it'll be fine and everyone will be able to see. So when we looked around, we found that there are no suitable data sets to actually consistently evaluate the few-shot methods in the framework that I've set out. And in fact, variations of the few-shot methods had been tried here and there in this context. So for instance, there were two separate publications which had tried to use MAML, but because there are completely different set of tasks used in testing and training, and it really matters precisely which task you're addressing, as we've seen in my earlier plots, it was really difficult to actually make any kind of comparison between them to know whether or not which method was actually working the best. So while many different calculated physical property data sets exist, this is the same as doing this protein ligand binding prediction. We needed something that actually represents that. And to meet the objectives, it became clear that this is actually a requirement and it's actually relevant to a real world problem. It's something that needs to be fixed. And so I went about making this data set with the intention of making it available to the wider community, and to really set a position from where we hoped that people would be able to start working on this problem. But it needs to be something that can be trusted by the pharmaceutical industry as much as machine learning community, because otherwise its impact is going to be somewhat limited on the pharmaceutical perspective. So I set about making such a data set and benchmark, using a lot of pharmaceutical chemist input to effectively query Kemble, which is an open database of pharmaceutical data of this kind of activity labels of different ligands against different targets, lots of cleaning, filtering, and steps, and then a careful separation into few shot, train, test, and validation sets. So this is the task sets. So there ends up with 5,000 training tasks, 100 and wait, how many? I forget now. I think 40 validation tasks and 150 testing tasks. So this is the eventual data set, and there's built an infrastructure around it to make it widely accessible, and defined a benchmarking procedure, which I encourage you, if you're interested in this work, to go and take a look at. And the advantage of all this is that now the drug discovery community has access to state-of-the-art ML approaches on data that they believe is an accurate representation of the work that they actually do on drug discovery projects. And it's been set up in such a way that it's easy to implement new approaches within the framework. And I wanted to set it out as a challenge to the machine learning community. Let's make it possible to do better on these tasks. So the question is, how well did we do on these tasks? So let's look at the mean performance across all of our testing tasks, specifically in the case of just the single task models. So the models are only given access to the training data for that particular target protein. There's no pre-training, and here's what we get. So as before, the overall performance is not fantastic. It's certainly very much degraded when realistically small amounts of data are available to the model. Again, I really want to highlight just how good in comparison to everything else random forests always turn out being. Random forests operating on fingerprints are surprisingly effective for this kind of task. But what happens if we try few-shot learning methods? So here we are now including all of the different methods that I discussed before that had been trained on our training set, and then and a validation set indeed, and then tested on our testing tasks. So we have here mammal operating on top of a GNN model. We have a multitask model that I mentioned operating on top of GNNs. We still have random forest position here. And here we have a prototypical network model that consumes or operates on top of, if you like, a GNN model, and at the same time this is concatenated with fingerprints as an input as well. So this uses both representations side by side. And this performs actually surprisingly well. And we can look at the distribution of performance across tasks. So this plot is just showing the mean, but if we look at the distribution, we see that basically the performance across the different tasks is very task dependent. Some tasks gain a huge amount from being presented with models that have been pre-trained. And in other tasks, this doesn't help at all.
So a question here.
Yeah.
Are all of the neural networks using fingerprints as well as the graph representation?
All of the neural networks.
Or is it only the prototypical network which is using the...
Right, yes. So basically this plot represents the best in class for each of the classes. So in the mammal and the multitask case, the fingerprint setting wasn't adding anything. So that's not included. Yeah. Sorry,
Right.
that's the,
No, and then the fingerprint is concatenated to the output representation from the GNN backbone.
Yeah.
Right. So the prototypes are computed on these concatenation. Is that
yes,
how I should?
yeah.
Thank you.
Yeah. There is also an intermediate small MLP layer, but yes. Hi.
Is there an ablation of the prototypical network here? What things are contributing the most?
Which things are contributing to the most? So we did do a small amount of ablation on this, and we found that I really do. It's really disappointing to me, but it's definitely the case that in this particular instance, the fingerprints were causing the largest uplift. I think if you add in the GNN component, and we tried a lot of different forms of GNN, it only gives you a tiny increase in performance at the end of the day, which is a shame. I mean, not tiny, but it's not as significant as you might hope. So a sort of side point to all of this from my perspective is GNNs are not some kind of magic bullet is what I would actually say. But yeah. Yes, so sorry, I think I've gotten out of sync. The slide that you can all see at the moment has 2 plots, is that correct?
Yes.
Yeah.
Good. Okay. I also mentioned neural processes. This is more just flagging it if there's anyone in the audience with a special interest in neural processes, rather than going into any details because I'm conscious of time. I did try them. I found that the mean performance ended up being no better than prototypical networks. So certainly there wasn't any particularly strong reason that these should be used instead, but I thought it was worth including this for completeness, given that I discussed the possibility of that being the right approach. Another good question to ask is, does the training data volume matter? So how many tasks you're including in this set of pre-training tasks? And what we see is actually, and so this is the overall performance on the testing tasks when they are supplied with 16 data points, dependent on the amount of data available in the training set, in the pre-training set. And what you see is you do have an increase in the performance. So in other words, the more training data you can supply in some sense, the better your performance will get. You're gaining something from all of this. What's quite interesting, and I don't yet have a very strong or good explanation for, is that prototypical networks need slightly less data before you get a better performance. So to summarize, random forests with fingerprints are pretty good. They're not quite good enough, but with a few data points, you can win by using some meta-learning or few-shot learning techniques, in other words. Prototypical networks have so far been overlooked in this field, but it turns out that they work really well. And finally, I would say that while many of these techniques are kind of actually not that complicated, the thing that really gets in the way of making progress is having the right data set and the right benchmark so that you can actually make quick comparisons and clear comparisons. Yeah, and so that's basically everything I wanted to say. I'm just gonna, I think, skip over this, say thank you all for listening. I wanted to also say thanks to my colleagues who were involved in different ways in this work. So we have Mark, Christoph, John, Marvin, and Sarah from Microsoft. And this was also work in collaboration with Novartis, with Nadine, Jessica, and Hubert. Yeah, and so if anyone has any questions, I'm very happy to take them. I think I see a hand.
Yeah. Thank you, Megan. It was very nice presentation. You mentioned about some IC50 or KI/KD, some value converted in a binary. How I see as a chemoinformatician, these binding values reflect not only the ligand, but also the structure of receptor. There is concept of solvation. And I think if we only give a graph representation of a drug to address the problem of a binding, we are giving kind of incomplete information. And in my opinion, or in your opinion, do you think giving an active site of a protein structure would be more complete representation of a given phenomena to predict the binding?
Yeah, I completely agree with everything you're saying. And it's one of my personal almost criticisms of the current state of this QSAR setting, which is that it tends to ignore the actual target that's being addressed. Having said that, it is how pharmaceutical chemists often seem to work, because they don't always know precisely what the binding, the active site looks like. They don't have a huge amount of information about it. And so from that perspective, you know, this is in the kind of the realistic everyday setting. But I agree with you that ideally what you should do is have a model that consumes a representation of the binding site. The other thing I didn't talk about so much that I think is really relevant, especially in this kind of few shot learning setting, is that the relationship between all of the tasks that are included is not very well defined. So you have this thing where you've just thrown a bunch of data in from 5,000 different protein targets, and some of those will be relevant and some of them aren't. And it's a known problem that we don't know exactly how to relate one task to another. But in this case, we do actually have some information. So there's been some recent work released showing that you can take protein sequences and use those as a way of relating one task to another and then improving your multitask predictions. But yeah, no, I completely agree with you. In general, you would hope to include that kind of information. It's just the realistic setting is often not that.
Yeah, thank you. If you're going to use a sequence, I would suggest don't use sequence as a one-dimensional string. Try to use some 3D information, because the binding involves a hydrophobic interaction.
Yeah,
You've shown a multitask with several of receptors. So the hydrogen bond only hold the ligand in a receptor, but the binding is usually exhibited by this hydrophobic interaction. That's why you need a 3D information of a receptor, where you will know which parts of a ligand not touching the part of a receptor. So there is a lack of hydrophobic interaction within those parts. And there are receptors which gives they touch very well to the ligand and exhibit quite a well hydrophobic interaction.
Yeah, I completely agree. I should say that I didn't do the work. It's not my group that did the work with the sequential or using the sequence as the additional information. I agree with you. I think in reality, you want a nice representation somehow of the 3D binding pocket. There has been a little bit of work doing this, but as I say, it's not, you know, it's not the setting that kind of at the time that we felt we were addressing, because we were trying to, you know, solve this simple problem. But I agree with you very much so that this is the correct way of doing it.
Thank you.
So I'll take over from there. So a question regarding pre-training tasks. You mentioned a bit self-supervised pre-training tasks.
Mm-hmm.
Did you? I didn't catch if you compared to those in this work.
Yes, I did, but I didn't actually highlight it very strongly. So let me just here. Yes, we're showing the right one here.
All right,
sorry.
there is.
Yes. So this is the pre-train here.
This is structural pre-training tasks, so context prediction or masked.
Yeah. And this is, you know, this was actually the very first thing I ever tried, and I have to say it was somewhat disappointing. But I kind of feel like the reason that this isn't necessarily working particularly well in this setting is because what this teaches a model to do is know roughly what chemistry looks like. It doesn't teach it anything about how to recognize similarity between molecules in a way that's relevant for binding, which is what prototypical networks are really good for.
Right, thank you.
Yeah, I have a question slash comment. The comment in continuation what Swapnil asked. So if we imagine, for example, toxicity or off-target effects, there this very often a lot is known already. So then one could perhaps include the structure of the target, respectively have more training data to begin with.
Mm-hmm, mm-hmm.
Although then the question is, how would that compare to just, let's say, a regular model, whatever, random forest or neural network model? Would there even be a point to do then this type of one-shot training if you have a lot of data?
Yeah, so basically when you have these known targets which cause toxic effects, my understanding is that there is a huge amount of data already. They have already trained models which they consider to be, when I say they, I mean chemists that work very close to the ground on this, or computational chemists that work very close to the ground, that they consider to be already sufficiently accurate without actually adding in additional structural information about the target. Because I suppose, I guess if you're not in the few shot setting, the question is, or you're not in this sort of multiple task pre-training setting, what are you gaining by adding the additional structural information in?
Yeah.
So what you're effectively then saying is, I expect to learn something of, let's say, the physics, that somehow the model is learning to use this information to improve its prediction on the task. Whereas if you're using it in the few shot setting, what you're doing is you're allowing it to recognize the similarities between the targets, and say, then these two targets were quite similar, so therefore I know that I should use this aspect of the model, let's say. I mean, that's a bit vague, but in the very specific setting, for instance, of film layers, where what you're doing is you're effectively using a hypernetwork acting on some additional information about the task to set the values of parameters in your network so that it picks out specific features based on similarities of tasks. So that's one idea of how you can incorporate target information. But if you're not in the few shot setting, it's not so clear how it is useful.
Okay, yeah. And then another question, have you considered, are you looking into using this for reactivity, a synthesis prediction, or something, making molecules, so to say?
So the overall idea behind having quite specific local property prediction models is to include them in the generative setting when you're generating molecular ideas. So by synthesis models, you mean models that predict synthesis pathways to a final molecule, or what exactly do you mean here?
Yeah, that would be probably the long shot. If we just take it more simple, just one step, A plus B giving C, so would that be at all possible, for example? Because there is synthesis, there is a lot, it's a similar situation. There can be either a lot of information, then it's obvious for a chemist, they don't even need a model to say, or there could be very little precedence, and then the question is, well, would it work or not?
I see. I guess what's more challenging there is how would you actually separate? So you're taking a bunch of data about, here are all of the reactions that have worked that we know of, and using that to train a reaction prediction model. The question is that clearly delineated into multiple tasks? How exactly would you get that to set it up in that setting, I think is the question. I don't know. I mean, is it easy to separate out all of the different reaction types in that way into different sets of types of reaction? Because if it was, then yes, you could possibly use that in this way.
Okay.
Yeah.
So if there's time for one more question, let's see. Yes, so the discretization you do for the binding affinity values.
Yeah.
Is the reason that the prototypical network needs to have label data, or sorry, categorical targets. If I understand the predictable networks correctly, the prototypes are derived from the labels, essentially.
Yes. Yes, so prototypical networks are useful in the, sorry, let me just skip back to the diagram here somewhere. Useful in this kind of binary or multi-class label setting. That's usually how that's how they're set up. Neural processes are very similar, and you would usually use them more commonly for regression.
Because intuitively, I would think that instead of discretizing the binding affinity value to actually predict it directly would give more information to the model. Because right now, you know, the threshold chosen, some ligands may be very close to it, some might be very far away, and we're throwing this information away, essentially.
Yeah.
Or is that correct, that intuition?
Yes, I agree with you in general that would be, you would hope that would provide much more information and be, in that sense, an easier modeling task. In practice, the data available in Kemble is quite messy and quite noisy, and there are lots of features that make it rather unusual, such as having limited dynamic range in the reported measurements. So lots of the measurements end up all piled up at the 10,000 nanomolar point, which is not actually reflective of what's going on. But yes, I agree that in principle you could sort of dive deeper into that and make a better modeling problem.
Thank you very much, and thanks for an excellent presentation.
No problem.
Really enjoyed it.
Really enjoyed it. Thank you.
Thank you.
Okay. So do we have one last question? Otherwise, just thank you, Megan, for a really nice presentation. Next week, we're sort of continuing this theme with machine learning for the sciences. Magnus Röding is going to talk about microstructures and mass transport in porous materials. So welcome back next week.
Thank you. Thank you, everyone.
Thank you. Goodbye.
Bye-bye.